Welcome to today's class. Today we'll be speaking about laws of motion. These laws of motion were designed by Sir Isaac Newton. There are three laws of motion. The first law states that every body will continue to be in state of rest or of uniform motion unless and until it is disturbed by an external force. What do you understand by this? Suppose a body is left at rest, lifetime it will be at rest. If a body is in motion, lifetime it will be in motion. For example, I'll tell you. Say you kept a pad on the table in a room and you locked it. You came after 2 days, right? When you open the door, pad should be found at the same place, and Sir Isaac Newton is saying the same thing, that pad will be seen at the same position because you left it, it remained at rest. So when you came back, it will be found at the same position. Same way, if you go to a ground and if you kick a football, for lifetime the ball will move. It will continuously move, he is saying. As such, there is nothing wrong in this. But what is happening in case of ball is reversing, isn't it? If you kick a football, after traveling to a certain distance, it will stop. Why did it stop? Because some external force has acted on it, and that is frictional force. He is saying the same thing. If some external force act on it, then automatically it will stop. Otherwise, it will not stop. In the first example, you opened the door after 3 days and pad is not found on the chair. Say it is lying down on the ground. It may happen because some external force might have acted on it. That is the reason pad is not seen at the same position where you left it. Right? This is what he is saying. If a body is at rest, lifetime it will be at rest. If a body is in motion, lifetime it will be at motion. If you don't find these two happening as it is, then some external force might have acted on it. Such an easy thing, isn't it? So the same thing, this law has an extension called as inertia. Inertia, in simple words to understand, is it does not accept the change. Suppose you are sitting in a bus takes a start, move front. We lean back. See, inertia means it does not accept the change. Why students answer it wrong? I don't understand. See, if I say bus is moving front, immediately you have to say that we will lean back because it is inertia, does not accept the change. Suppose moving bus suddenly stop. We lean front because our body does not accept this change. Now, why I will tell you. Suppose say you are traveling from one place to other. Say a place A is a place and you are traveling to a place B. Say the distance between A and B is 60 kilometer. So you started at 1 o'clock. You started at 1 o'clock and reached this place at 2 o'clock. You reached this place at 2 o'clock. Can you tell me your speed? Speed is distance by time. So it is 60 kilometer per hour. That is your speed. Yeah. So you are sitting in a bus which is having a speed of 60 kilometer per hour. Can you tell me what is your speed? Most of the students say that you are not doing any work in the bus, isn't it? You are simply sitting in the bus. Therefore, you feel that your velocity or speed is zero. It's a blind mistake, isn't it? How can it be like that? Tell me. At 1 o'clock, you are at a place called A. At 2 o'clock, you are at a place called B, which is at a distance of 60 kilometer. If you say your velocity or speed is zero, then you should remain at A. How can you come at B at 2 o'clock? How can you find yourself at position B at 2 o'clock? Impossible, isn't it, if you say your velocity or speed is zero? So make the changes in your mind. You are in the bus, whatever the speed that bus possesses, you also possess the same velocity or speed. Now, when we speak about this, there are two things we come across. One is rest, other one is motion. Excellent definitions about rest and motion is given by Sir Isaac Newton. You know what do you mean by rest? Rest means if there is no change in the position of a body with respect to time. See, I started the class, now almost 10 minutes over. For a duration of 10 minutes, did you find any change in my position? I'm here only. No. You found me here previously before 10 minutes. Now, after 10 minutes, also, I'm in front of you at the same position. So, with respect to this 10 minutes, my position did not change. I may be moving here and there here only. That there is a movement of my body, but position when I speak, it did not change. If there is no change in position with respect to time, it's an excellent definition I can say. That is called body is at rest. Suppose there is change in position of a body with respect to time. See, there is a change in position of the body. Body was at A, now it is at B. With respect to time, it has traveled for a period of 1 hour. There is a change in the position of the body with respect to time. That means that bus is in motion and it had velocity and speed. Did you understand? If there is no change in position with respect to time, then the body is said to be at rest. If there is change in position with respect to time, then it is called motion. Suppose you are sitting in the bus, right? Just beside the driver. Driver is working, he is working, okay, he is on duty. You are just sitting beside the driver. Conductor is in the bus, other passengers also in the bus. With respect to all that is there in the bus, with respect to all that is there in the bus, when I mean driver, conductor, passengers, the bags, luggages, what you kept in the bus, everything with respect to all this, you are at rest. With respect to you, other things are also at rest. How? You are in the bus was at point A. After 1 hour, it has reached a point B. But what happens inside the bus? Everything remained at their own position with respect to you. Within the bus, everything is said to be at rest. If you compare yourself, or if you compare the driver or the conductor or your luggage and the bus also with outside surrounding, then you are said to be at motion. Why? Because you might have come across a tree at point A. You might have come across a tree which is at A place A. Now it is not there with you. You have reached a place called B. So with respect to that tree, you are at motion. With respect to you, tree is also at motion. Remember, most of them get confused. With respect to tree, okay, you have traveled away from the tree because tree was at point A and now you are at point B. You can say you are at motion. But what happened with respect to the tree, you are at motion. With respect to you, the tree is also at motion because it is left at A. This is what interesting is rest and motion. Excellent, isn't it? So this is what first class says. I feel that this first class should be in class 6th. Everybody should know Newton laws at earlier at possible. So they should be in 6th class. Why? Inertia. So moving bus suddenly move front, we lean back. A moving bus suddenly stop, we lean front. Now I think you got the answer. Why a moving bus suddenly stop, we lean front? Why? Because when the bus is moving, it is moving with, say, with the speed of 60 km per hour. You are also in the bus. Your velocity is same. As I said, no. If you say your velocity is 0, you will be found at A. So it is understood now. Bus is having velocity means you are also having velocity because you are also in the bus. Bus being a mechanical device, by application of brake, it stops. But what happened to your body? It will not stop. When you are in the bus is having a speed of 60 km per hour, your body is also having a speed of 60 km per hour. So suddenly when the bus stopped, your body will not stop. That's the reason we lean front. Again, when the bus suddenly move front, again we lean back. We don't accept that change. You know the interesting thing? When the bus takes a left turn, we lean right. When the bus takes a right turn, we lean left. These are things happening to you, not an issue, very simple, you are not at danger. But interesting thing about inertia. Suppose you want to get into a moving bus. Dear students, please kindly remember this. Educate others and you get educated also. If you are if you want to get into a moving bus, say the bus is moving in this direction, you want to get into that bus, right? Don't, first of all, don't take your life into risk, but I am teaching you what? Laws of motion. Therefore I am taking the example, that's all. right? So bus is moving this direction. You want to get into a bus which is moving. You know the interesting thing, your position also should be in the direction of the bus. It should be like this. Bus is moving this way, your position also should be in the same direction. Now the staircase is coming. Previously staircase is say 2 meters away from you. You didn't go for it. You waited here. No problem. Bus has come. You just catch hold of the bar and you can simply get into the moving bus. Why? The reason is what? You are in the position of the bus, right? Never, suppose say you want to get into a train, which just started moving. Say the staircase is at 5 meters from you and you're waiting for that staircase, and by the time staircase came, if you catch hold of the bar like this, no, you'll fall down. This will be the position because you're not in the right position in one. But if you can take it like this and wait for the staircase like this, the moment staircase come, you need to jog a little. Jog a little. Why? What is the reason to jog? Jogging little bit. Why? Because you said no, train is moving. That means train is having some velocity. You should also possess that velocity. You should have the same velocity what the train is having. Then you will be at comfort taking what train, getting into the train. These are very important things. You might have seen people coming out from a moving train or moving bus suddenly before it stops. Say the bus is going to stop at a distance of 5 meters, just 5 meters. Some of the students, youngsters, teens, they try to get down from the bus before it stops. No problem, nothing to worry. But the thing is what? Same, you should take the direction. Your face should have the direction of the movement of the bus. Bus is moving this direction, so you should also take the same position. So when you get down, you should not stand. Simply after getting down, if you stand like this, you will fall down because you are coming out of a moving bus. What does it mean? You are coming out of a moving bus, isn't it? That bus is having some velocity, say 5 kilometer per hour, very less one, but still that is the velocity. And your body also possesses the same velocity because you are coming out from the same bus. Just now I said no. If you are at a 1 o'clock at A and 2 o'clock you are at B, which is at a distance of 60, and within 1 hour you reach that place, means whatever the bus is having velocity, that same velocity you are also possessing. So since you are coming out of a running bus, you need to jog for a while. That's all. If you jog for a while, slowly your velocity will reduce and become zero. That's the actual reason. Same thing is, see, everything, Newton's first law, inertia, is implemented in athletics, sports, 100%. You might have seen people, spinners like Kumble, right? In the past, bowling, cricket, they ball. They take a small run. They don't take a big run. They take just a small run. So suppose actually what happens today? See, I am a bowler, cricket bowler. I took the ball. I am standing just like this and I took the ball. What is the velocity of the ball? Zero. Please don't say other answers. I am not moving, isn't it? So the ball velocity also will be same velocity what I possess. I just said I am just standing and I took the ball. The velocity of the ball and velocity of myself will be same. Now I started running. A spinner, how much he runs? He runs a short distance, very short distance, a distance of say 2 to 3 meters, not more than that. Therefore, when he started running, he is having some velocity. That same velocity will be possessed by the ball. Therefore, he will apply a little bit of muscular energy and he will ball may travel with the speed of 90 kilometer per hour or say maximum 100 kilometer per hour. That's all. Now take Malinga. All our Indian players, yeah, we don't, let us not have anything in our mind. Everybody is a player. Javagal Srinath, right? Kapil Dev. Just take them. They used to have a run. They used to have a run, long run. Pace bowlers run for a while. They run near about 15 yards. For what they run? If they take the ball in their hand, they stand, the velocity is zero, they started running, they run. Slowly they gain the velocity. They gain the velocity near about 80 km per hour. That is the speed they run. So ball is also with them. Ball is also having the same velocity. So before bowling, what happens? They apply little bit of energy to that one and they ball with the speed of 150, 160 and 180 also. These are the things happening, and all that is due to sports. See, a javelin throw. Just imagine a sports person. He want to throw a javelin. He takes a run. Why? Suppose he is catching a javelin in his hand and he is standing like this. His velocity is zero. Javelin velocity also will be zero. Therefore, he starts running. He want to gain velocity. Whatever the velocity he is possessing, since he is catching hold of the javelin, javelin will also have the same velocity. But a line will be drawn. If you stamp that line or step out of the line, that will be considered as foul. Therefore, before that, he has to leave this javelin and all that. He has to stop and leave all this. See, suddenly after running for a while, can you stop? You cannot stop your body. How the body stops, man? Your body cannot stop. The reason is what? Inertia. You're running, isn't it? So it's having some velocity. Suddenly, if you want to stop, it will not stop, because since you're already traveling in the moving bus suddenly stop, your body moves front. Same thing is implemented in javelin. But a line is drawn, you're not supposed to run. So you balance yourself by what? Leaving all this velocity into the javelin. See, sports is related to that one. Okay. Now, this we have finished first law first. Now I want to support your what you call first law with an activity. It's a simple activity. Everybody can perform this one. You take a glass tumbler. You take a glass tumbler. You place the glass tumbler over the table. Over the table. Okay. You put a cardboard. You put a cardboard over the glass tumbler. Place a coin over here. 5 rupees or 10 rupees coin over here. You flick this card, tap, you flick this card, or else pull the card or push the card. Okay, what happens? Can you tell me? Most of the students think that if I pull this cardboard or push this cardboard, okay, most of them think that this coin will come along the card. No, no, nothing. It doesn't happen like that. When you flick this card moves away. Okay, and the coin falls directly into the glass tumbler. Why? Because it is at rest. It is at rest. It does not accept this change. You're flicking the card, isn't it? It does not accept that change. That is the reason coin falls into the tumbler. You know the very interesting thing about Newton's first law of motion, that is inertia. How many things are happening due to inertia? Do you know? At our home, you see, mother, after sweeping the house, she will take the broomstick and hit it to a pillar or something. What does it mean? Tell me. Some dust particle remain in that broom. So when she is hitting it to the pillar or something, okay, what happens? Those dust particles does not accept that change. Therefore, they fall down. If you didn't understand, I'll give you one more example. Interesting example. You want to plug the goas and you're not able to catch that goa, and because you want to pluck it, you are not able to catch it. It's at a long distance. What do? Can you tell me? We take the branch, we catch hold of the branch, we at least see that branch is caught by us. Now we just shake the branch. This shaking, this change is not accepted by that goa. Therefore goa falls down. You might have played in your childhood, isn't it? Asking your friends, we just look at the tree like this during winter, and other people also come and say, "What happened? What is on the tree like that?" And suddenly we shake the branch and run away from there, and water falls on them. Why? And water molecules, mist and fog and all that, okay, did not accept the change what you did, so they fall down. Since there are so many actually, so many examples in our day-to-day life we come across. Okay, this is all about inertia. Now, continuation we'll see Newton's second law of motion. So, before going into second law of motion, it is very important for everybody to know about momentum. Right? Momentum is represented P bar, because momentum is a vector quantity. Momentum is mass into velocity. Momentum is mass into velocity. Both play a great role. Momentum, mass plays the great role. Velocity also plays a great role. Do you know the interesting thing? Suppose say there's a bicycle with a mass of 10 kg and a car is there whose mass is say 3 tons. Both are traveling with the same speed and they are hitting a wall, just a wall. Which one you think will damage the wall more? Tell me. It will be car. I said very clearly that velocity is same. I maintained velocity is same, but mass I said it is different. So which has struck hardly to the wall? It is car. See, momentum plays a vital role. Now, momentum, when you speak about mass into velocity, it's a product of these two. Now, CGS unit and MKS unit, you come across CGS unit, MKS unit. This is mass, as you said. These are written according to length, mass, and time. So, mass, you said, isn't it? So, it's gram. Velocity means it is actually what distance by time or displacement by time. Displacement by time means length by time. So this is a CGS unit of momentum. If you speak about MKS unit of momentum, mass isn't it? So it's kg. Velocity is what? Displacement by time or distance by time or length by time. Length by time. These are the units of momentum. Don't feel difficult in writing the units. It is so simple. It is. You just need to know what actually the physical quantity says about. It is telling about mass and velocity. So mass unit in CGS is gram. In MKS it is kg. Velocity means it is displacement by time or distance by time. Displacement or distance, nothing but length by time. So it is centimeter per second in CGS system. In MKS it is meter per second. Right now, I finished momentum, isn't it? Momentum is a product of mass and velocity. Now I will tell you what second law means. Second law, it's written like this. F is proportional to m v minus u by t. Right? How to read it, very interesting to read. You read from down. Remember, always you have to read it from down. This is called rate. According to physics, it is called rate. Rate of change of momentum. Now, what do you mean by change of momentum? Momentum is what? Mass into velocity. But I want to know change in velocity, because velocities are of two types, isn't it? Final and initial. So I want to write it like this. Momentum is equal to mass into v minus u. This is another formula for momentum. Okay, therefore this is change in momentum. Okay, but I am speaking about rate of change of momentum is directly proportional to net force. This is what you mean by Newton's second law of motion. So I let me write like this. F is equal to, so I need a constant because I removed proportionality. So it is F m v minus u by t. What do you understand by acceleration? Acceleration is v minus u by t. Therefore, all this is replaced with k is a constant. You can remove it. Therefore, this is what you mean by Newton's second law of motion. Rate of change of momentum. Momentum, once again, I am telling you, this is nothing but mass into velocity. This is nothing but change in velocity. Nothing but mass into velocity. Rate of change of momentum is directly proportional to net force. So when I take it as is equal to, I get a constant, but doesn't make any difference. It is m delta v by delta by t. V minus u by t is a. Therefore, this is Newton's second law of motion. F is equal to ma. Now, the other things you should understand, okay? See, like Galileo has performed an experiment, said like this. Suppose there's a steep slope like this. You are allowing the ball to move front. What happens? Tell me to its acceleration. Acceleration will be less. So it decreases as it goes up. Its acceleration will decrease. The other way, he has dropped a ball from here to down. So steep edge, isn't it? What happens in this case? Acceleration, it will be more. In this case, acceleration will be more. In this case, acceleration will be less. So from point of acceleration, right? From the point of acceleration, let us see Newton's second law of motion. From the point of acceleration, see, acceleration is directly proportional to force. If you apply more force, more acceleration will be created. If you apply less force, less acceleration will be created. Suppose in front of me two blocks of mass is there, 2 kg, 2 kg. In one of them, I am applying 10 Newton of force. In the other one, I am applying 20 Newton of force. Which one you think will move fast? 20 Newton. So acceleration is directly proportional to force. Other case, acceleration is inversely proportional to mass. Suppose say I am having two objects like this. One is say 1 kg, other one is 2 kg. I am applying same amount of force. I am applying same amount of force. Okay. Which one you think will have more acceleration? Quite natural. Less one will have more acceleration. Okay, less one will have more acceleration because mass I am speaking about mass. Okay, so acceleration is inversely proportional to mass. But what did I speak about here? Force. I am speaking about force. Why not? Acceleration is directly proportional to force. That means if you write here acceleration or F, it means same. F is inversely proportional to mass, right? If the mass is more and you want same acceleration, then your force has to double, force has to increase. That's what I mean. If you want the acceleration possessed by this body and this body to remain same, I need to double the force over here because it's 1 kg and 2 kg. I need to double the force. If I want same acceleration, that means your acceleration is inversely proportional to mass and acceleration is directly proportional to force. These two are friends, so their common enemy will be m, mass. So same thing, right? Let us take this as 2. From these two, what do you understand? A is proportional to F by m. Means A is directly proportional to force and A is inversely proportional to mass. Let me remove this proportionality, so I'll get a K constant F by m. So K constant, let it be aside. Now what is left over? A is equal to F by m. Cross multiply. F is equal to ma. Back again we are the same derivation. So see, rate of change in momentum is directly proportional to net force. Nothing but, right? You got it as F is equal to ma. If you start from acceleration point, everybody knows more the acceleration, and more the force, more will be the acceleration. So force is directly proportional to acceleration, or acceleration is directly proportional to force. And acceleration will be inversely proportional to mass. Same amount of force you are applying on two different objects of different mass, same amount of force, keep that in mind. Then automatically what happens? The one which is having lesser mass will have more acceleration. Okay, right. So lesser mass will have more acceleration means inversely proportional. Why? Because these two are friends. So at the place of here you can even write F. So A proportional to F, A is inversely proportional to mass, therefore A is proportional to F by m. And if I remove this proportionality, you get a K constant. That means A is equal to F by m. Cross multiply F is equal to ma. You got back your formula again, Newton's second law of motion. Now Atwood machine works on Newton's second law of motion. It also determines acceleration due to gravity. It's a simple machine, right? But one thing you should remember always, this Atwood machine will have two different masses. Okay, one will be lesser one and the other one will be more one. Not necessary this should be M2, M1 and this M2, it is left you. But remember one thing is what? One will be lesser mass, other one is more mass. And the other thing is, most of the students find this derivation difficult. As such, it is not difficult. You remember the techniques, what are involved in this Atwood machine. The technique is, tension experienced with a lesser mass will be more. Tension that is experienced by a lesser mass will be more. Tension experienced here will be more. Tension experienced here, it will be less. Then at tension when it is less, weight experienced by this will be more. Weight experienced by this is more. In my schooling, my teacher said the same thing. So what I did, since he said tension here is more, I made this T as bold one, big one. He said that weight here is more, I made it bold one. Now let us start the derivation. So T minus M2G is equal to M2A, equation 1. Second case, M1G is greater. So M1G minus T is equal to M1A. This is equation 2. Add up equation 1 and 2. What is equation 1? On the left side, T minus M2G is equation 1. What is on left side of equation 2? It's m1g minus t. Now, what is on equation 1 on the right side? M2a plus M1a for the second one. So, it's M a is common. So, let us take a. So, it's M2 plus M1, or you can write it as M1 plus M2. Right, good. This part is over. Now, here plus t and minus it gets cancelled. What is left over? Minus M2g, this one, okay, plus M1g. So I want to take G as common here. G into, so it's plus M1, isn't it? I'll take here, and minus M1, I'll maintain it, minus, sorry, yeah, M2 it is, M2G over here is equal to A into M1 plus M2. Right, finish. Now what happens? I want for equation for A. Along with A, what do you find? M1 plus M2. That goes denominator, and G into M1 minus M2. Okay, done. Now I want to substitute this A in one of these equations. So I am taking the first equation. I am substituting in for equation 1. T minus M2G is equal to M2A. At the place of A, I am going to substitute this type. This one, G into M1 minus M2 by M1 plus M2. Okay, done. This is the equation. Now, let me write down the same equation here. T minus M2G is equal to. Now, M2G into M1 is what? M1 M2G. Right? This part of multiplication is over. Next, plus into minus is minus. This is what? M2G into M2. So, it's M2 square G. Right? This part is over. By it's M1 plus M2, right? Now T is equal to, I want to send this M2G, since it is negative, I want to send to the other side, M2G it is, okay, plus M1 M2G, this remains as it is, minus M2 square G by M1 plus M2. Now here nothing is there, okay, so T is equal to, the LCM you find here is M1 plus M2. Now, how many times this 1 will go? Same times, m1 plus m2 times it will go, okay? 1 into m1 plus m2 is m1 plus m2. What is left over? You have to write down here, m2g. Same way this one, plus m1 m2g goes, sorry, this will go how many times? 1 time. So, it remains as it is, m1 m2g is, okay, minus m2 square g. Done. Now what shall we do? The T is equal to, that is multiply these two, M2G into M1, M1, M2G. This part is over, multiplication. Same way multiply M2G into M2. So it is M2 square G. Did you understand here? M1, M2G. These two, M2G, M2. So it is M2 square G plus, this remains as it is, M1, M2G minus M2 square G by M1 plus M2. This is negative, positive m2 square g, this is negative m2 square g, so these two terms get cancelled. What is left over? M1 m2g and M1 m2g, both are same, so 2 M1 m2g there. See, this is one M1 m2g and this is another M1 m2g, so 2 M1 m2g's, okay, by M1 plus M2. This is the formula to calculate tension. This is according to Atwood machine derivation it is, okay. Now we will see Newton's third law of motion. As everybody knows, every action has got equal and opposite reaction. So generally it is represented how? Newton's third law of motion. Every action has equal and opposite reaction. So generally reaction side we represent it as negative. This negative indicates that it is opposite, that's all. As such, you don't have anything negative. We represent reaction as negative, okay? So every action has equal and opposite reaction, Okay, now we'll speak about law of conservation of momentum, which works on Newton's third law of motion. Now let us discuss about law of conservation of momentum. See, momentum can neither be created nor destroyed. It disappears in one form and reappears in another form. It is similar to law of conservation of mass. It is similar to law of conservation of energy. So what did I do? See, I created a platform over here. I am rolling this M2 mass, remember M2 mass, with an initial velocity 5 meter per second. So I am rolling this mass, I am rolling it, okay, with the what speed? 5 meter per second. I took another mass, heavier mass, but I am rolling it with a speed of 20 meter per second. So what happens? This M2, M1, bigger one, will strike this M2 after certain period of time. So it's collision. This is called collision. Okay. Then what happens afterwards? They started traveling. They started moving with their own velocities. So initial velocity of M1 we considered as U1. Initial velocity of M2 we consider as U2. Initial. Now, final velocity of M1 is taken as V1, final velocity of M2 is taken as V2. Now, what is it? Momentum. Momentum, first of all, you should know what is momentum. Momentum is a product of mass and velocity. Momentum, it is represented with P. It's a product of what? Mass and velocity, right? So take this into consideration. So first marble, second marble, don't mix up. First is different, second is different. Momentum into mass into velocity. Why I took U? Because it is said that it is before collision, means initial, right? But yes, we got marble one, no, one and one. Same way for the second one, M2, U2, because you are speaking about it, same line it is, before collision, M2, U2. First collision, M1, U1. Why did we take M and U? Momentum is mass into velocity. So mass into velocity. Now momentum after collision is what now? M1, V1, M2, V2. See, two remain here, ones remain here. No mix up, because this is marble one and marble two. He is saying change in momentum. So generally we do V minus U, isn't it? V minus U is our change. So it will be now M1 V1 minus M1 U1. Same way for second marble, M2 V2 minus M2 U2. No mix up. One side, the other side, because this is all about marble one, this is all about marble two. Now what is a new term? It is added here, rate of. So this remains as it is, M1 V1 minus M1 U1 by T. Same way it is here, M2 V2 minus M2 U2 by T, because he is asking you to do rate of change of momentum. Already momentum you wrote, see, change in momentum you wrote. For that, rate of change of momentum only. Change of momentum remains as it is. So among these, one will be action, other one will be reaction. M1 V1, yes, okay, minus M1 U1 by T is equal to, every action has equal and opposite reaction. So reaction we generally mention negative in front. So it's M2 V2 minus M2 U2 by T. This T and this T gets cancelled. What is left over? M1 V1 minus M1 U1 is equal to, minus into plus is minus M2 V2, minus into minus is plus M2 U2. Now M1 V1 is positive, so let it be here. Here it is negative, isn't it? V, so we are making V terms one side and U terms the other side. So minus, if you bring this side, it will become plus. This part is over. This is already positive, M2 U2. So this is negative, isn't it? Take it to the other side, it becomes positive. This is the formula to calculate momentum before collision and momentum after collision. And you know, momentum before collision will be equal to momentum after collision.